Hi ladies and gentlemen, welcome to our last video for Math 344. Today what we're going to do is just work a couple of examples for the Markov questions that you can expect to see, and we're just going to start right into a couple of the questions that are on the worksheets that we'll be doing throughout the week. So this first one has to do with this problem on the first worksheet, and what we want to do is we're just going to take a look at a situation with a network where we have signals traveling from nodes 1, 2, and 3 around in these arcs. And the instructions tell us that we're going to follow the arcs with equal probability, and the signals have to move from one node to the next or one state to the next. They can't remain in the current state. So the first question is, what is the probability of a signal traveling from node 2 to node 1 in exactly 3 steps? And the hint it gives us says, well, how can we make that trip? So to go from node 2 up to node 1, we're going to take a look at the possible paths here. So we could go from 2 to 1, and then we could go from 1 to 3, and then we could go back to 1. So that's 3 steps. That's one possibility. We could go from 2 to 1, and then back to 2, and then over to 1. So that's a possibility. We could go from 2 to 3, and then we could go back to 2, and then we could go to 1. And really the only other option we have is to go 2 to 3 to 1, but if we do that, if we end up on node 1 on an even step, then we can't get there, right? So this is not going to work. So what we need to do is calculate the probabilities associated with each of these chains. Well, we know that the easier way to do this is to answer question 2 first, which is to create the transition matrix. And so let's do that. We want to set up the transition matrix P, and the recommendation is, of course, that you just put the numbers in. These are not numbers in the matrix. These are just the nodes so that we can keep track of the positions of the matrix. So the matrix itself is going to be inside of our square brackets. And what we want to do is we want to look at the image here, and we want to calculate what the probabilities are. So it tells us that during each step the signals have to move. So the probability of transferring, and remember the froms are on the rows and the twos are in the columns, so from 1 to 1 is 0. From 1 to 2, that's going to be 2 paths out of a possible 6. So this is 2/6. Don't feel like you need to simplify the fractions at this point. It's easier to do the kind of bookkeeping if you just leave the denominator in an easily identifiable mode. And then from 1 to 3 is 4 paths out of a total of 6 paths, leaving 1. 4 out of 6. So you can see that we have satisfied the requirement, the sum of the values in the row is equal to 1, right? So this sum is equal to 1. Okay, going from 2 to 1, still 2 paths, but now there are 5 paths. We have a total of 5 ways to get out of 2, so that's going to be 2 out of 5. No signals in 2 can stay in 2, and then from 2 to 3 we have 3 paths. So we have the 3 paths remaining there. Again, of course, this sums to 1. And then finally from 3, and you kind of see the flavor now, from 3 to 1 we have 4 out of a total of 7 paths, and then the other 3 paths go to 2, and we have no paths left to go from 3 to 3 because the signal has to move. It can't stay there. So this is the information, and we can answer the question in part 1 by taking the cube of this. But before we do that, let's make sure that we understand what's going on. So in order to transition from 2 to 1, that value is 2/5. This probability is 2/5. And then 1 to 3, from 1 to 3 is 4/6. And then finally from 3 to 1 is 4/7. So calculating, we have 30 times 7 is 210. So this particular path, the probability of us getting from 2 to 1 along that specific path is going to be 32 out of 210. Remember, those of you who have not yet learned, to calculate the probability for consecutive events all occurring, it's going to be multiplication of the probabilities. So the probability of rolling a 3 and then rolling another 3 is the probability of rolling one 3, which is 1 in 6, and then the probability of rolling a second 3, which is another 1 in 6, and we multiply those. The probability of rolling 3s in order like that is 1 in 36. So we could do that for each of these paths and calculate what the probability is for each path, and then we sum those probabilities together because we could have gone in any one of those 3 ways. Let's just do one more for completeness sake. So from 2 to 1 is 2/5, and then 1 to 2, that's 2/6, and then 2 to 1, of course, is another 2/5, and that would give me an 8 over 25 times 6 is 150. And then the third path has another probability. We just add those together. So in order to make that considerably easier, we're going to calculate p cubed, and this is the whole point of using the linear algebra. When we multiply by the p, we're doing those dot products and we're all set. So I have a live script over here. Let me take a second and enter the matrix. All right, I have the matrix here and I'll execute this. Want to make sure that our matrix is what we think it is. Remember, and this might come in useful, sometimes it is, sometimes it's not, but you can use the format rational in order to make these fractions. But we can see we have a 1/3, 2/3, 2/5, and 3/5, and then these are the sevenths here. So I've taken p cubed, that is the accumulation of 3 steps, and the resulting probability of going from node 2 to node 1 is this 30857. So the probability cubed, right? The probability, this is the transition matrix. In this case, it's a Markov matrix. Cubed at 2, 1 is equal to 0.30857. That's the probability associated with that question. So those are kind of introductory ideas. Now what we want to do is, it says given an initial signal of distribution of 100, 100, 100. So we're starting with this initial distribution of signals, and it's going to be 100 in each entry. And the question is, what is the p transpose times s naught, and what does it represent? So we just do that calculation straight out here. Enter this in. So I'm going to have p transpose times my s naught, which is 100, 100, 100. Executing, and I have this answer here, which I can just write down. So p transpose times the initial vector is equal to 97.143, 76.19, and 126.67. And the question is, what does this represent? So this represents the signal distribution after one step if I started with 100 signals in each node. So according to the probabilities, the signals have transitioned away from their nodes. They've crossed over each other, some of them from 2 to 1, some from 1 to 3, some from 3 to 1, etc. And this is the new distribution here. So then continuing with that idea, we have the last question. Given an initial distribution that's the same, what is p transpose 75 telling me? So what I want to do is I want to calculate p transpose 75 and show you what that is. So I'm going to go p transpose, and I'm going to raise that to the 75th power. And this is really an important point associated with the whole idea of the Markov matrices. So you can see down here what we have is we have a distribution that's the same for each of the columns. And if we multiply this now times our initial vector, I'll do a little copy paste here. What this is telling us is by the time we get to 75 steps, then we have reached an equilibrium. And the distribution of signals is right here. So the distribution for P transpose raised to the 75th power times our 100, 100, 100 beginning. We have 100 signals in node 1. We have 83rd.3, and then we have 116.6 with the vinculum. So this is the distribution, and this is the equilibrium distribution. Really important point here. It doesn't mean that the signals have gotten to those nodes and stopped. It just means from a probability standpoint, this is the expected distribution over a long period of time. So the signals, the 100 signals on average that are at node 1 are all leaving according to the probabilities, and the ones in node 2 are leaving, and the ones in node 3 are leaving. They're crossing over each other and going to the adjacent nodes in one step. But we've reached this position where the number of signals on step 76 is going to be expected as this distribution here. One more thing to just show you. So if we take and let me pull this up a little bit, make it a little easier to see. So what I'm going to do is I'm going to find the eigenvectors and eigenvalues for P transpose. So let me do an eig of P transpose, and we'll run this. Right? And what you can see is that we have a eigenvector associated with eigenvalue number 1. I always have a single eigenvalue here. So I have an eigenvector associated with eigenvalue number 1, right? And this is my steady state distribution. We have the negatives here, but of course we can multiply by -1. But if I take this first eigenvector, so I'm going to take x colon comma 1, and I multiply it times our vector of initial condition. I'm just doing it element by element multiplication, right? So I don't quite have the same setup as I have here, but I have the same ratios. I need to shift the eigenvector, right, so that I have a total of 300 signals, because right now I've lost signals. So the eigenvector points in the right direction, but it's not just plug and play. I can't just take it and slap it in and expect it to give me the right answer. I need to scale it so that I have the correct number. This was part of what we talked about during the first lesson, where the number of objects that's in our system, in this case in our network, has to remain the same throughout the entire process. So we would scale that. So we're going to take this and we're going to go with a negative, and then we can see what the scaling is. This is going to be really scaled by the first entry. Right? So we're going to divide by x1 comma 1, and we end up with this here. Oh, the x1 was negative, so I had the negative of the negative. Okay, and you can see that this matches our distribution. So the eigenvector points in the right direction for steady state, but we just can't just grab it and use it straight out. So that's the first example. Let's move on to the second example. This is a maze. This is a common type of situation that we have. And I'll just read this to you. Another problem we want to practice here. Develop a Markov matrix P for this maze. Mice are dropped in at A, B, C, and D. States E and F are intersections, and W is the water state. So the mice are working their way into the water, and once they get to the water, they're going to leave again. So consider the mice's movement to be entirely random at each intersection where the intersections are marked A through F. A mouse at position W will automatically move to F on the next step. And then it says a mouse will always move from its current location. So again, the probability of a mouse at A staying at A is equal to 0. So we set up the transition matrix. That's what we're after. Develop the, in this case, Markov matrix. Let me write down a framework for that. So here's what we're doing. I highly recommend that you always mark the states in both the columns and the rows in order to avoid making mistakes. It's very easy in this detail-oriented process to make a simple error. So we know A to A is 0, and now we have to calculate. So A can go to 1, 2, 3 different options, B, E, or C. And so all of our paths are equally likely. So we have a 1/3 to B, we have a 1/3 to C, and we have a 1/3 to E. There's no way to get to D directly. There's no way to get to F or W directly. And now we just continue the process. So B is A, F, and D. So I have A, I have F, and I have D. All the other nodes are just zeros. I'm going to keep filling this out. Actually, what I want to do is just jump down to the W. So it tells us in the instructions that the mouse at the water always goes to F. So that means I have a probability 1 that we're going to go to F. All the other probabilities in W, A, B, C, D, E, they're all equal to 0. I think I have miscounted there. F, water, A, B, C, D, E. No, that's correct. So let me fill in the rest of these. We'll do one more together. We'll do F together. So F, from F we can access B, D, E, or W. So we have 4 different options, so the probabilities are 1/4. So for F, we can go to B, we can go to D, we can go to E, or we can go to the water. So we can't go F to F, and we can't go to C or A. I'll finish filling this out. All right, so I have completed the Markov matrix here. It's worth noting a couple of facts. The columns do not sum to 1. All of the rows do sum to 1. The columns do not. Let's take a look specifically at the F column. So that's 1/3, 1/3, 1/3, 1. That totals 2. It doesn't need to total 1. It's worthwhile to make sure that you haven't made any mistakes to take a look. Let's take a look at F. It says that we can get 2F, because we're looking at the column, we can get 2F from nodes B, D, E, and W. B, D, E, and W. And that looks correct. Okay. So I think that this is solid for us, and now it says find the probability of a mouse moving from D to A in exactly 5 steps. We're not going to write down all the options, obviously. That's the whole point of using linear algebra. We're just going to put this matrix into the computer. So let me take a second and do that. All right, I have our matrix set up in here. One thing that I recommend, if you have larger matrices, you can do a carriage return. Instead of stringing these all together, you can do a carriage return, and you can set up the rows so that the matrix looks more like what you think it should when you're typing it in. And then, of course, you're going to check the output to make sure it's correct. And as I said, if you type in format rational, this will give us the output in fractions. And so we can just check to make sure that we have everything correct. Okay. Right. And you'll notice this matches exactly what we want right here. So getting to the water, there's only one way to get to the water, and that's from F. And when a mouse is at F, it has 1 chance in 4 of going in the direction of the water. That's just an easy way for us to take a look at that. All right, I'm going to cover that up. Notice that I commented out the earlier work that we did, better than deleting. You can just use the Control-R for a block comment. And now what I'm going to do is answer the question. Probability of moving from D to A in exactly 5 steps. So I want to calculate P5. This is my scheme. I just set it up this way to make it a little bit easier to do the calculations. So then it goes from D to A. So I've got A, B, C, D. So I have 31 out of 243 is my probability. If you want to see that as a decimal, that's no problem. We can change from format rational back to format short G. G meaning kind of a general, and it will select it. So I go down. Remember, the first column is 2, and I need from D to A, and that is 0. Right, so I have a P5, and I'm looking at 4, 1, that's D to A, and that's equal to 0.12757. All right, next question here, 3. Consider 10 mice at each starting position, A, B, C, and D. What is the expected distribution of mice among the 7 nodes after 6 steps? So we want to take a look at P transpose after 6 steps, and we want to multiply it times our initial vector, which has 10 mice at A, 10 at B, 10 at C, 10 at D. There are none at E, F, or at the water. And now we want to know, what is the distribution of mice look like for this situation here? Okay. So, easy enough. I have P transpose. I'm going to raise that to the 7th power. And then multiply times the initial distribution, which I will call R0. And let me just define an R0 here. R0 is equal to 10, 10, 10, 10, 0, 0, 0. And that's going to give me my initial vector, and then we'll do the multiplication. So let's run that. That looks correct. And so this is the distribution of mice right here. And we would just copy that vector down. I'm not going to write it down, but it's right here. And you can see it's reasonably evenly distributed. Looks like about 6 mice per the intersections except F. There's a larger number of mice at F, and that's because it's the water state is always going back to F. And it looks like there are about 2 mice at the water at any given time. So we started with 40 mice, and this is what the distribution looks like. So then it says, well, let's do the same thing, but we're going to start with 40 mice at B and see what it looks like. So we'll do exactly the same thing, except I'm going to replace this starting vector. I have 0 at A, 40 at B, and then 0 at C, D, and I have all the rest of the zeros. So everything else looks the same. I've just changed the starting vector. And we can verify 40 mice at B. And we can see that it's reasonably close to the same. It looks like B actually has fewer mice at it. And it looks like F has about 1 more mouse at it. The other values are pretty close to being the same with one another. And remember, we can raise this up to a much larger power, like 75, and nothing magical about 75. Let me put in another number. I'll put in 100. Raise this to a high power, and we'll see what the equilibrium distribution of mice looks like. So this is a really large number, and this is the equilibrium distribution of mice. There are 6 mice at every node, A through E, 8 at F, and 2 at the water. So even after just 6 steps, we were pretty close to that. Also remember, this is an equilibrium. It's not static. So the 6 mice at A are always going to be leaving on the next step. But we have mice that are going to be coming in from B and from C and from E that are going to make up for the 6 that are leaving. The 2 in W will always be going to F, and then of the 8 at F, 2 of those will be going to W. So it's all in equilibrium, not static. Last question. If a mouse starts at A, how many times is it expected to pass through intersection D in the first 30 steps? So the way we're going to answer this, and we're just going to approximate. There are actually a higher level when you get into more advanced, really OR classes. Some of you are in OR 312. This is the kind of question that you would answer in that class. Not this one specifically, but this type of question. So we're going to do just an approximation. What we're going to do is say, okay, a mouse starting in A, how many times is it going to pass through intersection D? Well, the equilibrium distribution. So let's just look at, because this all has to do with the equilibrium distribution. Let's just look at the probability matrix, the Markov matrix, raised to this really high power. And we can see what the transitions look like. Okay, so here's the the matrix, and we can see at equilibrium, no matter how many mice we have, then we're going to have 15% of the mice that are going to be in A and 15% in B, etc. 20% of them, right? So we got 10, 20, 30, 40, 50, 60, 70, 80, 90. That's 100% of the mice that are accounted for in this situation. So what we have is we have 15% of the mice are going to be in A. Well, the other way we can think about this, particularly when we're talking about Markov matrices that have an independent step of time, we can think about this the amount of time. So if we put one mouse in A and we let it start moving around and we discount the first 20 moves, or really the first couple of moves, then the amount of time that the mouse spends at each of these locations is dominated by, or is given by, the equilibrium. So it's going to spend 5% of its time at the water. So if each step is a certain period of time, like 5 seconds, and the mouse, and we track it for 100 steps, so for 500 seconds, then we would expect it to have spent 5% of its time at the water. That is the same kind of idea we can use about how many times the mouse actually went to the water. So if it went to the water 5% of the time, then the number of times it went to the water out of 100 steps would be 5, because it spent 5% of its time at the water. That's the idea we're going to use to answer this question. Okay. We're just going to take a look at the equilibrium, and then we're going to multiply that equilibrium times the number of steps to figure out how many times the mouse went there. And there's only one caveat to that. Let's do that calculation first. So how many times are we expected to pass through D? Well, so if we have 30 steps, what we're going to do then is we're going to take P transpose, and we're going to find out what the equilibrium is, and then we're going to multiply that times 30, and we're going to check to see what that number is. So let me show you what that gives us. We have 30 times P transpose, and of course this is going to give us a matrix, but each of the column vectors is representing the each of the column vectors is representing the equilibrium solution, so they're all the same. So we can see that we expect a mouse starting at A to have passed through D about 4.5 times. Okay. So of the 30 steps, about 4.5 of those steps were spent at location D. And then the next one is 100 steps, which is more easily divisible here. Let me answer that question. So it looks like about 15 of the 100 steps were spent at D. So the mouse is moving around, right? It's randomly moving around to different places, and 15 of those 100 steps, it's going to be at location D. So here's the only caveat, the only way to improve this very kind of crude estimate. It's not bad, it's not off by a lot, but it's not the precise mathematical way of doing this calculation. It is quite close, actually. But what we want to do is we want to realize that, hey, starting at A, we can't, in the first step, get to D. There's no way for us to actually get to D. So we can go A to B or E or C, but we can't get to D. So we really don't have 100 steps that we're talking about. We really have 99 steps. And I know this seems like a small adjustment. It's just a slight improvement to our approximation. We just are honest with ourselves and say, hey, the mouse can't get from A to D on the first step. So let's just talk about the 99 steps where the mouse could have gotten to D. And we can see that that drops off a little bit now to 14.85 visits. So that's our answer. So the answer here is really, this one was 4.5, but better is 29 times P transpose 100. And remember, the P transpose 100 is just giving me the equilibrium distribution. That's all I'm interested in. And that's equal to, and let me just run this. Now that you've seen it, you can certainly do it, 4.35. And it turns out that 4.35 is more accurate of an approximation than 4.5 when we're talking about 30 trips. Okay, that's it. And there are no questions for today. We're just going to do the worksheets. We're going to do the homework, get you a lot of practice so you're able to do this stuff when it comes time for the final midterm and the final project. Thanks.